Thank you. Well, as Nico said, that's what I will talk about. It is a paper we wrote with Marcus, Stefan Lucas, Luke, and Yuri, my supervisor. And it was basically to sum up what I have been doing and investigating in my first 2 years of the PhD. So the context is that when we want to see the memory of an object-oriented application, we see them as an object graph, where objects which are here in sequence point to other objects and compose what we call an object graph. So in my PhD, I tried to define what is a used object. And from my point of view, I call a used object an object which at some point it receives a message or somehow it is used. Because some options maybe are directly used by the VM, so it did not receive a really method invocation, but I consider them as used also. In the contrast, an unused object, it's an object which has been living in the image, but since in a while it didn't receive any message at all. So that I'm interested in those kind of objects. If we briefly see what the garbage collector does, the GC only collects the object that nobody else points to. So it works by reachability. If an object has no more in common reference, it will be garbage collected. However, and this is what I try to achieve in my PhD, is what happens with objects which may have not been used for a while, like for example F and J in this case. So can we do something with them? Can we swap them to this, for example, in order to just let in memory what we need, and then if someone in the future I need it, we will bring it back? So that's what I'm doing or trying to investigate in my PhD. This is the basic aspect. So what I'm trying to build is what we call an unused object manager. I don't know if you have a better name. So in the paper, we focus in three things. The first is, as I told you, we sum up the problems that we have found so far. Because there are really a lot of problems and they are not obvious, and it took me a lot of time to understand them. So I think it would be worth it to at least to document them, so if Pharo wants to do a future work, at least you can know the problems it will find. The second one is that we show non-working solutions, because one may think, but you have this problem, why don't you do this? No, it's not that easy. So for some of the problems that we show, we also explain why the obvious or submachines do not work. And finally, we show our first steps in our future possible solution that I will show you at the end. So, in a nutshell, in very few words, what it does, this unused object manager, is to detect some unused object, to swap it out, so then it replaces some object. We will see maybe it will be just the root of the graph, or maybe some other object will be replaced by proxies, and then we serialize the object that we want to swap, and we send it to a file or a network or somewhere outside the primary memory. Because our final goal is to use less memory. It's just to let in the image the objects that are already being used. And then the contrary process, which is swapping, is that when one of those processes may happen to receive a message, so something that I swap out, which finally at the end was needed, so the process intercepts the message and nods back what it was swapped out. So basically, I discovered that there could be some distinction, some subsystem inside this object manager, and we found that we have the object swapper takes the graph to swap out, replaces objects by proxies, and the serializing which serializes the object to a string. And then this could be maybe more in the future, but it's a tool to automatically detect an unused object, so that then we can know which object to swap. So this is basically a division that we find. It's not extremely in design or in code, but there's responsibility we found in the manager. So I will start to show you some of the sections that I grouped some problems in small sections so that you can see it. The first one is the first question when I try to do this. Imagine that on the left side we have the primary memory, in the right we have, for example, the disk. Imagine the secondary memory, and we have this graph. Imagine I have this graph. This is, I mean, in the memory, in the virtual machine, at the end there is a root table which has the pointer to the root, and then you have all the memory. So imagine I have this graph, which at the end it points somehow from the DM, and I want to swap C. Let's say that C wasn't used for a long time, so I want to swap it. So what I will do, I will just replace that option with a proxy, and I will write C on this. I will serialize it and I will put it on this. But what happened? The proxy does not point to F. The proxy is a small proxy that just stores the information in order to be able to load back or to swap it down. So the problem here is that if the garbage collector runs, this is the garbage collector, we will lose F. But I serialize only C. I didn't serialize F. I didn't serialize the whole graph. So the conclusion that we got at the very beginning is that we cannot just create one proxy per object that we want to swap. So it's just swapping objects individually do not work, because I lose objects because of the garbage collector reachability, and otherwise I could make the proxy point to the other object, but in that case it will be the same amount of memory that they use, the proxy and the target object. So I won't release memory. So the conclusion is that to really be able to use that memory, we need to group and swap out several objects altogether so that we can use less proxies for them. Okay? The second thing was that while doing experiment, we discovered that there are a lot of options that we cannot just swap. But the idea that the system will eventually, hopefully, work automatically. So we can just take randomly some part of the memory and detect an innocent object. But it's not that easy, because if you try to swap some of these objects, you will for sure crash the game. So there are a lot of things that you cannot swap, and you need to be careful. But the problem is that there's no documentation that says, okay, yes, this little object, you cannot swap it. So it's like kind of investigate which object should I not swap. Then there are special classes, because ideally the option manager should swap any kind of object. In smalltalk, the good thing is that classes are objects as well. So if a class has not been used for a while, I could swap it also, because at the end it's an object. But there are certain classes, or if you want to say it, instances of the meta class, which I cannot swap. For example, proto object, RY, symbol, etc., etc. Because these are classes that are used maybe directly from the VM, or maybe they're used for every smallest possible code execution. So it's not possible, or we don't want to swap them. And then it's, of course, that we cannot swap out what we need to swap in, or to swap out again. And it looks stupid, but it's very difficult to know which option do I use to swap in. Because there's not a static analysis I can do for that. Because I can say, okay, yes, to swap in I need my code. But the code at right times goes by different paths. So how can I be sure that an option that I randomly choose will be needed to swap in? So that's another problem. So what we found is that we should somehow specify a list of classes or options that we should not swap. Okay? And then I will show you what we are doing in our first solution. So if we now talk about the proxies and regarding the memory usage about them, the first thing is that how do we implement proxies? The first approach we always see in smalltalk is to use the not understand. That's the obvious solution. The problem is that first, if we do not understand, all the messages that are understand want to be intercepted. So that means that if I have a proxy, if I send a message that the proxy understands, it won't load back the graph from this. So for the client user, it will be something wrong because the proxy will be answering instead of the real object. So the client code will have different path. So it's really necessary to be able to intercept as much messages as possible. Then there are some other messages that we cannot drop, like if nil, if not nil, if true or false, blah blah blah, because these are inline by the compiler. So these methods are directly replaced by bytecodes, so they are not executed. So if I have a proxy and you see if nil, then it's the same. I cannot intercept that. But likely, in my case, you can imagine that the proxy is to replace an object that I want to swap. And it's not likely, these methods are implemented mostly in or small integers or true and false. It's not very common that I need to replace those instances with the proxy, because as I will show you later, most of the time what I just need to replace by the option are the roots of the graph. And booleans and small integers are not roots. So mostly the instances of the receiver of this method won't become or replaced by a proxy. So after all, it's not such a big problem. I'm not sure if it's really complicated. Then there are even more methods that I cannot execute, I cannot intercept. The first one is a class. Class has a special bytecode, so it means that the method is not executed. So, for example, if an object was replaced by a proxy, and we have this code, after replacing an object by a proxy, this will go in a different path from what it should. So that's why we need to intercept as much possible messages as possible. If the proxy answer instead of forwarding, that's a problem from the client code. This one was easy. I can just remove the optimization from the compiler. So the compiler, when it finds class, it doesn't set the special bytecode. And the overhead lost with that it's only 4%. So it's not a problem for my prototype that I am building. The problem is equal. Equal is not, it's not executed because so it is a special bytecode for equal, but equal cannot be not optimized. So class, I can remove the bytecode optimization, but equal cannot. There are several reasons. One reason is that it is demonstrated. I talked with one guy in Brussels, with Steph Mark, it's a guy behind working with that. He showed me with a kind of theorem that equal has to be, it cannot be a real method executor. If you want, I can provide you the link. And even more, even if I forget that, in Pharo it's also very complicated because a lot of code of Pharo uses equal as a way to avoid generating an execution point in the VM so that it can switch processes in the scheduler. So forget that, it doesn't matter. Anyway, in my concrete solution, this is not a problem, the equal. Why? If I told you that I replaced the target object by a proxy. To do that, I use the become to swap them. So it means that all of the pointers that were pointing to a specific object will point to the proxy. And all that were pointing to the proxy will point to the original. So at the end, it doesn't matter because this will continue to be correct. Because if an object, for example, was replaced by a proxy, then this will be equal because this one, since I don't get it, also was updated. So at the end, it will always do what it should. So it's not a problem for me, luckily. So the lesson that I learned here is that I cannot replace instances of true, false, block closure, and small integer with proxies, because of what I told you that otherwise I'm not able to intercept messages, and some other reason that the VM don't like to change that. And one, there is that some optimization at class should be disabled so that I can intercept and forward to the target object. Now, imagine that with the previous example, I have the proxy for C, okay, perfect. C was written into a file or something, in a database or somewhere, and this proxy needs to somehow have the address of C. Imagine that now a person will receive a message. He needs to go and materialize that. So, what do I store here? What is this line? It is a file name. I mean, C is put in a separate file name. So here is called the file name. Or I have a table in secondary memory, and here is just store an index, for example. But that will mean that I will have to do compactation and all what the file system does, like FAT. Or it is an ID. Maybe each object has an ID, and I have a table which I can map IDs to addresses in secondary memory. So that's one of the things. The second one is where I store C. I don't know, I get one file per option that I swap, I put them all together in the same file, and then I store the offset, or maybe I can put them in a database instead of a file, etc. So, sorry, this is usually called a pointer SWIZZLING. This is a term that is very used in object databases, which means mapping from OOPs from primary memory to addresses in secondary memory. So what they mean is that I need to somehow map between the two sides, and the second one is how I will store the object in a database or altogether, separated, etc. Another problem is that to be efficient, I need to use, proxies we need to use as less memory as possible, because if the proxy uses almost the same of what I swap, I want to release memory. And so what you have to do is store the minimal information that you need. And even if you could do some optimization to use less, it would be really good. From that side, there's another alternative, which would be to use proxies as immediate objects. Immediate objects, it's what I call immediate object. It's objects that are directly encoded in the memory address. Like in script Pharo, you have a small integer, which the last bit in a memory address says whether in the rest 31 bits it's an OOP or a small integer. We could also, if we would have more bits, we could tag that the memory address is not a real OOP but a proxy. So we can encode there the address in secondary memory. This is what Gemstone does, for example. In Gemstone, when an object is on disk and there are objects from primary memory pointing to them, there is a special tag in the last bit of the memory address that says that is a proxy or that the object is on disk. So in the other bits, they have an offset in a table and they bring back the object from secondary memory. The thing is that this changes completely the solution. The algorithm to solve the swapping is completely different if you verify proxies of object or if you update preferences. So the lesson is that, of course, to really be efficient, we have to make proxies use as less as we can. Another problem is that imagine now we come back to the example and let's say I put names to the object of the example. Let's say that this object is John, which is an instance of user. Okay? So this object will be pointing to its class. It's not a real pointer, it's not an instance variable, but at the end, this object in the VM representation has a pointer to its class. So if I do the become, for example, because I wanted to swap the class user, it means that Sean's instance in his object header, its pointer to its class will be pointed to the proxy. So if now I do Sean foo, this will crash immediately because you can try it if you want. Try it, and this makes sense because it could be maybe solved by the VM, but basically when the VM does the method lookup, it assumes that the method dictionary is var number 2. And since here I put a proxy, which even maybe it doesn't even have an instance variable, or maybe it has 2 or 1. So the VM trying to access to the slot number 2, where he knows that the method dictionary is, and that crashes. And that's why you cannot add an instance variable to object, because that will it will add one instance variable, so the offset will all be moved. So at the end, the behavior, which has the format, the method dictionary, and format method dictionary, and okay, I don't remember the third instance variable. So it will move one of the slots, so the VM will crash. So that's why you're going to add instance variable to object, for example. So what we need is that we cannot just become any kind of object, because we will again have crashes or non-desired situations. So what we will try to do, idea is to create special proxies where we know that the VM or whatever can go wrong. The problem, of course, is always how to know that, because it's not written anywhere what you can become and what you cannot, for example. And the last section I want to talk, which is the most complicated, but I won't go in details. If you're interested in the topic, you should read the paper. But here is an overview of the paper. So I tell you that my idea is to be able to swap out graph. Because if I have graph, I could say, for example, let's say that I want to swap all these graphs, subgraph C, E, and F, because imagine 3 of them are unused. If I could do that, I can just put one proxy. I serialize the whole subgraph, okay, and just then one proxy. Then when the garbage collector runs, those E and F will be garbage collected, which is what I want. So this way I use less memory and I have everything I need on this. It sounds easy and it seems to work. However, that's the next slide. So my conclusion that it would be very interesting to be able to swap subgraph of objects. First, because I use less memory because I just need proxies for the root. And all of the other objects would be garbage collected. Still, there is a problem I will show next week. And the second reason is that I think I couldn't demonstrate it, just my good feeling, that when you have an object graph, if one of the objects is needed, most of it is probably that the other object of the graph will be needed as well. And if one of the objects is not used of this one, it's probably that the other is not used either. So what I mean is that when they use together. So if I am able to swap that way of subgraph, it could be interesting from that point of view. But of course there is a problem, it's not easy. So what happens if I now have this situation? Exactly the previous one. But I have incoming pointers from outside of the graph that you want to swap. What I do with this link, with this arrow. And this is extremely complicated because if I do this, for example, I am doing exactly what I did in the previous example. And the garbage collector runs, it will shut garbage collect E. F will still exist, but F was serialized also. So now if the proxy receives a message, it will materialize this. So I will get a duplicate of F. So C will be pointing to a different F, not the same instance. So So my question, I call this shared object, which are referencing from inside the graph that you want to swap, but also from outside. So the first question is if I should swap them or not. There are two possibilities. Maybe it's okay that I let this option, and somehow when I materialize this, I say, I know F, I already have a new version of you. So I just ignore what I materialize, and I make the materialized C to point to the already existing F. That means that I need to keep an array in memory that points real object, I need to use extra memory for that. But I did it. In one of my solutions, that is working. But the other point of view could be, if it's not used, so I don't care if it's also pointed from there, I want to swap it. That would be another point of view. So that's why I wonder if I should swap or not share the object. The second one is, okay, let's say that I swap it. Do we create proxy? Because if I swap it, what do I do with this reference? I mean, D has to point to something. So then it means that I would also need to create proxies for the shared object, not only for the root. So we need a proxy for F if I want to swap F. So it turned to be a little bit more complicated. And the most complicated, not complicated, it's complicated to do it efficiently. It's how you come to detect that an object is shared. It's no way to do it fast in Pharo or any VM, because you don't have a backpointer. I mean, you cannot, F doesn't store who points to it. So the only way is to scan the whole memory and see who points to F. But I should do that for each of the objects that are inside of the graph. So that is terribly slow. So my biggest problem is the correct handling and efficient of shared option, which sounds easy, but it's the most complicated task that I have been doing so far. But this is more advanced, so if you are interested, you should read the paper for the details, because I present some alternatives to solve that. So the lesson is, again, that it's very difficult. That's the lesson, sorry. Well, I will show you what I have been doing as a first steps. So if we remember what I told you about the subsystems, well, my project is called MAREA. It is because it is implemented in Pharo, and because the MAREA is tidy in S, which all the time brings from one side to the other one, from the sea to the beach, all the time constantly, and that's what I would like to do. And MAREA is the whole process, which I call it. So if I analyze the subsystems, first I start from this one. This is the tool to detect unused objects. I will explain you in the next slide the very overview. Then I create a better proxy implementation that does not understand, but instead it uses another hook provided by the VM, which is much more efficient than the does not understand. Then I didn't implement, but I help a lot Martin to use Fuel, because since I want to serialize everything, I want to be able to serialize context, compiling method classes, etc. I need a really complete serializer and fast. And this part, well, this is what is in progress, and hopefully I will find something useful. But it's still in development. This is the most complicated part, so I had already done the first, but I still need to solve the real problem. That is what I showed you at the end. So, very briefly, the unused object is a fork of the code VM. A fork, or if you want to say it in another word, it's just the VM that with some changes that I did. Basically, I did two things. First, to modify the object header of the VM so that I can use a special bit in order to mark when an object is used or not. I call that the user bit. And the second change is to intercept the method execution so that they set the bit on when an object receives a message or when it is used directly by the VM. And as a consequence, I could do some cool interesting stuff. So for example, I can enable the discovery, then I can do something, whatever you want to do or to analyze, and then I can stop and get the statistics. So here I can see, for example, the total images I have in the image, the total amount of objects, and the percentage of used objects, which means for all these objects that I have in the image, how many have been used when I did this? And I did this at the very beginning because I wanted to be sure if it was worth it all the effort. And we have a paper in the Smalltalks of last year, and there you can see that we did some visualizations with moose. For example, Esteban once gave me an image of small birds, ibis dog, I think. We run I navigate the whole website with Seaside, and only 4% of the usage of the objects were used. Only 4%. So that tells us that there could be a lot of objects that are referenced somehow but not really used in most of the cases. So then, as I told you, the proxifier, as I told you, I didn't use it, I don't understand. And then I use a hook which is called cannot interpret, which I won't explain here, but basically it lets me intercept all messages except the ones that I already told you which are optimized by the compiler. But all the ones are intercepted, not only the ones that are not understood. And the good thing with this proxy that I did is that I can also create proxies for classes and compiling methods, for example. So in the case that I told you that the VM crashed because I did a decom between an object and a proxy, I have special proxies that has the shape that the VM expects so that they don't crash. And okay, some additional thing, like I try to use very small memory in the proxies, and I do it very stratified in the sense that you have a proxy for one side, a handler for another one, and so I think that from the design point of view, it's nice. And so if you want, we have another paper in ISU this year, and if you want to read, you can read. It's very interesting, the hook that we use, the cannot interpret for intercepted messages. So eventually you can read it. Pharo, Martin already talked yesterday, so I won't say much. It was very good for me because I could extend fuel and change subclass and do some changes to optimize my own code. So I can, for example, join in the graph traversal and do something while traversing the graph, and things like that. I could easily make fuel, for example, to serialize proxies without sending messages to the proxy, because it's the serializer sends message to the proxy, we try to load it back when it is being serialized. So it's kind of complicated. So we have a paper in ISU this year also if you want to see more detail. And the option 12 is still what I need to solve, which is the real core of this, that is the more complicated part. And I need to see an efficient way to solve the problem with shared object. We have two possible solutions. The problem may be the speed, or maybe the amount of memory we use in order to support that. So we're still in development. And then the very last step is which graph to swap out. So how can I automatically detect which subgraph to swap, and when I decide to swap it. So that's all. If you have questions.